Hi everyone, welcome to our fourth and final lecture on solutions. This is the last part of chapter 13. So today we are going to talk about colligative properties. So colligative properties are properties that depends on the number of solute particles that have been dissolved. Doesn't matter what the particles are, but it's how many of them you have dissolved in a particular amount of your solvent. So here are some common colligative properties that came in whatever order they wanted, apparently. The first one is boiling point elevation. So if you have a solution, right, so you have some solute that's been dissolved in your solvent, you will have a higher boiling point than just your solvent by itself. So like if you have water, right, water boils at 100 degrees Celsius. But if you have an aqueous solution where you've dissolved something in your water, then now your solution will have a higher boiling point than your pure solvent. So it'll boil at, 102 degrees Celsius instead of 100. Freezing point depression is, the opposite. So solutions will have lower freezing points than your pure solvent. So water water freezes at 0 degrees Celsius. So if you have a solution, so you have some solute dissolved in there, you may have it freeze at temperatures that are lower than 0 degrees Celsius, so maybe -2 or -3 or something like that. And then vapor pressure lowering. So if you have a solution, most times solutions will have a lower vapor pressure than a pure solvent. I think we're also going to talk about sometimes when they will have a higher, but most times it's going to have a lower vapor pressure than your pure solvent, especially if you dissolve a solid in your liquid. If you dissolve two liquids, then kind of varies. So colligative properties, we use this particular equation. So our change in temperature is going to be equal to M times K, where M is not your mass, but this is your molality. And molality is not one that we talked about last time. It's the one that I said we were going to leave for this particular section because we're going to use it, a lot. So our change in temperature, the amount that your temperature will be different from your normal boiling point or your normal melting point will be your molality times K. And this K can be either Kf, which is our freezing point constant, or Kb, which is our boiling point constant. So in this equation, most times I'll just leave it as K, so that we can use the same equation throughout. So our change in temperature is going to equal to our molality times K. And so most times you'll see me write this molality as a cursive M, so that we don't get it confused with molarity or mass or all of the other M's we've got going on. Okay, so let's get moving. So molality is a little bit different of a calculation. Most times we have like our solute over our solution, just in general, whether that's grams or moles or liters or whatever it is. It's usually solute over solution. Molality is different, so make yourself a note. This is different. This is moles of solute per kilogram of solvent. Nothing to do with the solution. I mean, these are both in it, right? But it's if this is a solid dissolved in a liquid, it's essentially your solid over your liquid. So it's not, moles of solute over kilograms of solution where you're adding them together. Now it's just looking at, say, your water or whatever it is. So our example problem here is, what is the molality of a solution prepared by dissolving 0.1 moles of starch in 0.5 kilograms of water? So this is a really straightforward example, right? Our moles of our solute, our starch, will go on the top, and our water is our solvent. Most times water is our solvent. Will go on the bottom. So we would just divide those up. Our moles of our solute over our kilograms of our solvent, and we would get our molality. And again, most times we would put this and then put what the solute is. So 0.20 mole starch, which I know is a little bit strange to say. Here's another one. What is the molality of a solution prepared by dissolving 2.70 grams of methanol in 25 grams of water? Okay, so again, we're going to need to take our grams of methanol, which is our solute, and turn it into moles. So we take our grams, we use the molar mass, and we will get moles of our solute. And then we can take our grams of water, right? We divide by 1,000, and we will get our kilograms of water, right, which is our solvent. And so we do our moles of our solute divided by our kilograms of our solvent, and we will get our molality. And again, we'll usually report this with our solute. So pretty straightforward. Moles of solute over kilograms of solvent. Like I said, the thing that trips people up, make sure you don't do kilograms of solution. So we can use this molality calculation when we are determining boiling point elevation or freezing point depression, right? So here's an example. What is the boiling point of a solution prepared by dissolving 0.1 moles of sugar in 0.5 kilograms of water? We have boiling point of water. So our boiling point of water we're going to use is exact. Just in general, you can have as many decimal points as you want. Usually I'll just show it here as 2, but that's exact because that's how we're defining the temperature scale for Celsius. And then we have our KB for water. So this is our boiling point constant for water is given there. So we calculate our molality first off. So we have 0.1 moles over 0.5 kilograms of water. And we would get that this is 0.2 molal sugar. Okay, and after we calculate the molality, then we can go ahead and calculate our change in temperature. So our change in temperature is going to equal our molality times our KB, right? So up here, this equation up here, molality times K. So we take our molality, multiply that by our KB value, our molalities cancel, and we get degrees Celsius. So you're not done though, right? This is how much the temperature changed. Okay, and so we are looking at boiling point elevation. So since it's boiling point elevation, right, this will make the boiling point higher, right? And so we will add 0.1 to our existing boiling point for water. So we have 100 degrees Celsius plus 0.1 degrees Celsius gives us 100.1 degrees Celsius. So that would be the boiling point of this solution. So again, by adding sugar to our water, we allowed it to boil at a temperature higher than that which water normally boils at. Let's try another. So this one says, what is the boiling point of an aqueous solution that is 4 molal in solute? So it's already given to us, the molality, which is very nice of them. So we can go ahead and calculate our change in temperature. And so again, our change in temperature, right? Our change in temperature is always going to equal molality times K. So we have our KB value, we have our molality, so we can just multiply those together, we get our change in temperature. Again, we're still doing boiling point elevation, so this will get added to our normal boiling point of water. So we'll do our 100 plus 2.05, gives us 102.05 degrees Celsius. Pretty straightforward. Freezing point depression works just the same way, except instead of adding it, right, instead of where we were adding like 100 plus 2.05 degrees Celsius, this is freezing point depression. It will lower the melting point, right? It will lower the freezing point. So we will always subtract them. So you'll do 0 minus whatever your change in temperature is. So it says, what is the freezing point of solution prepared by dissolving 0.1 moles of sugar in 0.5 kilograms of water? So this is the same scenario, except instead of trying to find the boiling point, now we're trying to find the freezing point. So we can calculate our molality just like we did before. We get 0.2 molal sugar. And so then to calculate our change in temperature, we'll take our molality, we'll multiply it by Kf instead of Kb, right? Kf for freezing, and we will get our change in temperature. So now, instead of adding, like I was saying before, this is freezing point depression. So we will take 0 degrees Celsius and we will subtract our change in temperature, which gets us negative 0.37 degrees Celsius. So still not rocket science here, but we need to make sure, you know, if you're doing boiling point, you're always going to add your change in temperature. If you're doing freezing point, you're going to subtract your change in temperature. So we need to keep those straight. So here's another one. What is the freezing point of 100 grams of C2H6O2 dissolved in 200 grams of water? Okay, so first we're going to need to calculate our moles of our solute. So we'll take our 100 grams We'll divide that by the molar mass, and we will get our moles of our solute. And remember, molality is always moles of solute over kilograms of solvent. So we're going to pretend, I know that this isn't exact here. Apparently I was playing fast and loose with our sig figs. But let's say for now that this is 200 grams. And so we'll get 0.200 kilograms of water. Okay, so we'll take our moles of our solute, divide by our kilograms of water, and we will get our molality of our solution. Okay, once we have our molality, then we can multiply it by our Kf value, right? Because we're doing our freezing point, so Kf, not Kb. Take our molality, we'll multiply it by Kf, and we will get our change in temperature, which is a very large change in temperature. And again, we're doing freezing point depression. So we're going to take our 0 degrees Celsius that it would normally freeze at. We'll subtract 15, and we'll get negative 15 degrees Celsius. This is very useful, this freezing point depression. If you live, which we don't, but if you lived somewhere where it snowed, then, you know, that's why they salt the roads and things like that. By adding salt to the roads, they're lowering the freezing point of the ice, right? And so instead of freezing at 0 degrees Celsius, depending on how much of the salt that they add, they can cause it to freeze at a lower temperature, which means at 0 degrees Celsius, instead of being ice all over the roads, it's now going to be water, which is much easier to drive in than ice and snow. So there you go, practical application. So we have all of these so far have been, if you've noticed, covalent molecules, which do not dissociate in water. But we do have some compounds, right, ionic compounds, which do dissociate in water. And so we will, you know, call these electrolytes and non-electrolytes. Electrolytes is just a term for something that can conduct electric current when in aqueous solution, i.e. an ionic compound, right? All ionic compounds are electrolytes. They dissociate into ions, and they can conduct electric currents. So if you see this term electrolyte, really we're just looking for ionic compounds. Whereas non-electrolytes are most times going to be covalent molecules because they don't dissociate. And like I said, the only thing that makes it this whole electrolyte, right, we have these free ions, and they can cause or allow electricity to flow through the solution. So some examples, electrolytes that you've heard of, right? Gatorade, they're always like, it's full of electrolytes. Yeah, it has ions in it. It's got sodium and potassium and things like that. And salt water. Salt water would also be an electrolyte. So if you're dehydrated after your run, you could drink salt water. Not as yummy as Gatorade. But there you go. But the things that these have in common, right? They have dissolved ions. Whereas if we use the term non-electrolyte, that would be something that doesn't conduct an electric current. So covalent compounds, compounds with carbon. So my example here is sugar water, right? Sugar water, sugar is a covalent molecule. It doesn't dissociate. It stays together and floats around as the sugar. So it doesn't have free ions, and it won't conduct electric current. So the reason that we're talking about this is that if you have an ionic compound, right, a salt of some kind, remember that the term salt is used kind of synonymously with ionic compounds. It just means, salt just means ionic compound. And so these are things that can dissociate into more than two ions, right, two or three or whatever it is. And so the reason for this is that these colligative properties are depending on the amount of stuff that you dissolve. So like if I dissolve sodium chloride, right, if I put, 1 mole of sodium chloride into 1 liter of solution, right? Okay, yeah, it makes 1 molar sodium chloride, but it's not 1 molar of ions because each one of those sodium chlorides breaks into 1 sodium and 1 chlorine. So yes, we may have put 1 mole of sodium chloride in there, but that gave us 1 mole of Na plus and 1 mole of Cl minus. So we actually have 2 moles of ions floating around in that 1 liter of solution. So we have 2 molar of ions, which matters when we're doing these colligative properties because they will act independently. So that's why we use things like salts, or we use, a lot of times they'll use calcium chloride to depress the freezing point of water, like out on the roads, right? They'll salt the roads with calcium chloride, because for every 1 mole of calcium chloride you stuck in there, it broke into 1 mole of calcium and 2 moles of chlorines. So total, you have 3 moles of ions floating around in, say, 1 liter of solution. And so we are getting 3 moles of ions. And again, that matters because we are going to look for moles of stuff for these colligative properties. So if you have something that breaks apart into more pieces, then it can depress the freezing point lower or elevate that boiling point higher. So this is going to matter. So the ones that we did before, those we assumed that they don't break into pieces, which they don't. They were all covalent molecules. But moving forward, you need to make sure that when you're doing these calculations, think, is this an ionic compound? Is it a covalent molecule? Will it break apart when I put it in water, or will it not? So, again, colligative properties depend on the amount of stuff, right? The number of moles of dissolved particles present. So, if you have something that breaks into pieces, right, then you need to figure out, okay, well, how many moles of pieces do I have floating around in my solvent? Okay, so here's how this looks. What is the boiling point elevation for a 1.5 mole aqueous solution of calcium chloride? Okay, so this 1.5 mole, right, is telling you that's how much calcium chloride I put in there. But that's not necessarily telling you how many moles of stuff you have floating around. How many moles of ions do you have floating around in your solution? Okay, well, we know, right, that calcium chloride is going to break into 3 pieces, right? Just like we were talking about before, that calcium chloride solid is going to break into calcium and 2 chlorine. So we have 3 moles of ions floating around. So instead of using this 1.5 mole calcium chloride, for every 1 mole of calcium chloride we stuck in there, we have 3 moles of ions. So really, this is 4.5 mole of ions floating around. That's what we want to use in this calculation. So when we go through and we calculate the change in the freezing point, we're going to use how many, the molality of the ions, not of the molecule itself, but of the ions, because we care what's floating around in solution. So take the 4.5 mole, multiply by its, Kb value here. What are we doing? Boiling point. This should be change in boiling point. Multiply by the Kb value, we'll get 2.3 degrees Celsius. And then again, you can, add that to 100 and say, okay, it's going to boil at 102.3 degrees Celsius. That would be our new boiling point of our solution. Okay. But again, you need to make sure that you don't miss this step, right? Because you might, going fast, you'll be like, I see the molality. I've got my Kb. I'll multiply them together and get my, delta T, and I'll add it or subtract it, right? But don't skip this step where you have to see, is my compound, is it an ionic compound? Is it a covalent molecule? Will it break into pieces? Will I put it into water, or will it not, right? And how many pieces will it break into? So don't forget that step. Very, very important. So here's an example. What is the boiling point of a 2 mole aqueous solution of sodium chloride? So it has the Kb value for water there. So if we have 2.5 or 2 mole aqueous solution of sodium chloride, again, we should recognize, okay, sodium chloride is an electrolyte. It has 2 moles of ions, right? Because if I stick sodium chloride in water, then it's going to break into Na plus and Cl minus. So there are 2 ions for every 1 mole of sodium chloride that I put in there. So if I have 2 mole, that came in funny order. But if I have 2 mole sodium chloride, right, then for each one of those, I get 2 moles of ions. So really, this is 4 mole ions that we have in there. And then we can calculate then our change in temperature using that value as our molality. And we'll do our 4, times 0.512, and gets us our change in temperature there. And then we can add it and do all of the steps that we've been doing before. But again, this is the new step, right? So for ionic compounds, you need to think about how many pieces does it break into, multiply that by the molality if it's been given already. All right, on to the next thing. So this is Raoult's law. So this is the presence of a non-volatile solute. So we've talked about this term, volatile and non-volatile solutes, right? So if we have a non-volatile solute, this is typically like a solid. This would be like you added some sodium chloride, or you added something that's not going to evaporate at room temperature, right? We would think it would be weird if you had a pile of salt on the table and over time it started to evaporate, right? That sounds ridiculous. That is like a non-volatile solute, whereas like water or methanol or acetone or something like that, those would be volatile solutes, things that will easily dissolve. But a non-volatile solute, like a solid, will lower the vapor pressure of the solvent. And the way that we calculate this is the pressure of our solution, right? So the pressure, this is with, with the solid added, will be the mole fraction of your solvent times the normal vapor pressure of your solvent. So P naught, that's P0, this is essentially the normal one, the typical vapor pressure. So P of your solution is the observed vapor pressure of the solution. Again, that's with the solid in there. Chi solvent will be the mole fraction of the solvent, which means that you're going to put your moles of solvent over moles of solute plus moles of solvent. Okay, that would be our mole fraction of our solvent. And then P naught would be our vapor pressure of the pure solvent. So just whatever the vapor pressure of it normally is. Okay, and that's something you can look up. So here we go. Here's our example problem. This one says, what is the vapor pressure of an aqueous solution that has a solute mole fraction of 0.100, and the vapor pressure of water is 25.756 millimeters of mercury at 25 degrees Celsius. So we know things about mole fractions. If you'll remember way back from when we did gases, we talked about this a lot, but our mole fractions will always add up to 1. And that's kind of like, percents always add up to 100. So if we say, okay, we've got 1 point and a bunch of zeros is equal to the mole fraction of our solute, plus the mole fraction of our solvent. So we have the mole fraction of our solute. We need the mole fraction of our solvent. So we can just plug that in, right? 1.0000 and our solute. And so then rearranging, we can find that our mole fraction of our solvent is equal to 0.9, that didn't make it any better, 0.000, right? That would be the mole fraction of our solvent. And so we can find the vapor pressure of our solution, right? Because our vapor pressure of our solution is going to equal the mole fraction of our solvent times our, normal pressure of our solvent. So we can go ahead and calculate that out because we have both of those things. So 0.9000 times the vapor pressure of pure water, 25.756. Multiply that out, and we will get 23.18 millimeters of mercury. And here, it doesn't matter if you're going to do these calculations in millimeters of mercury or torr or atmospheres. Just make sure you're consistent throughout. Let's try another one. So this one says, what is the vapor pressure at 25 degrees Celsius of a solution composed of 42.71 grams of naphthalene, which is a non-volatile solute, so we know that our vapor pressure will be lower, and ethanol at, and ethanol. So we have the vapor pressure of pure ethanol is 25 degrees Celsius is 96 torr. So essentially what we have here is we have some naphthalene that we dissolved in our ethanol, right? Our solvent. And we're trying to figure out what's the vapor pressure of our solution. So naphthalene is our solute, and ethanol is our solvent. Okay. So again, we remember that, the vapor pressure of our solution is going to equal to our chi of our solvent times the vapor pressure of our solvent. So here, we have a lot of information already. We have grams of both things, so we can go through and calculate moles of both things, so that we can calculate our mole fraction of our solvent, and then we can plug it into this equation. So we have 42.71 grams of naphthalene, which I'm just going to abbreviate there as NAP. And it gives us the molar mass, 128 grams of naphthalene and 1 mole. So we are getting 0.334 moles of naphthalene. And then we can do the same thing with our ethanol. We have 40.65 grams of ethanol. And we know the molar mass there, 46.02 grams of ethanol per 1 mole of ethanol. And that will get us 0.883 moles of ethanol. So again, we need to have our mole fraction of our solvent, which means the moles of the solvent will go on the top, 0.883 over our total moles. So 0.334 plus 0.883. And that will get us 0.726, which is the mole fraction of our solvent. So again, it's moles of ethanol over total moles. And then to get the vapor pressure, vapor pressure of our solution, we are going to take our mole fraction, 0.726, and we are going to multiply that by our normal vapor pressure of our solvent, which is 96 torr. And that will get us 70 torr. So again, adding a non-volatile solute is lowering our vapor pressure. So there you are. Let's try another one. The vapor pressure of pure water is 23.8 millimeters of mercury at 25 degrees Celsius. What is the vapor pressure of 2.50 molar sugar? Okay, so we have moles of sugar, which is great. We have our vapor pressure of our pure water. We don't have a lot of other information though. First thing that we need to remember is that if we have 2.50 molar C6H12O6, that means we are having 2.50 moles of C6H12O6 over 1 liter, essentially, of water. A small amount of this, and I should have put something here like assume the volume of the solution is the same as the volume of water or something like that, right? Because otherwise it's not super fair. But here, so this is really 1 liter of our solution, but 2.5 moles of sugar is actually not going to take up very much space, maybe a milliliter or 2 kind of a thing. So we can assume that most of this volume, this 1 liter, most of that is coming from our water. A very small amount of it is sugar, which is why I was saying, I should have written something like assume, the volume of the solution is, the volume of the solvent, something like that. So if it shows up on a quiz or a test, know that I will do that. But here, like I said, we can assume because, most of the volume is water, we're just going to use that. So we have 2.50 moles of sugar, and then we can take this 1 liter of solution, and we're going to use that as our 1 liter of water. And we say, okay, well, I know for every 1 liter of water, right, I have 1,000 milliliters of water. And the density of water allows us to convert 1 milliliter of water into 1 gram of water. And then we can go through and we can use the molar mass of water to change that into moles. So like I said, a little bit of a jump, like I said here, but once you figure out the volume, you should be able to do the rest of this. And so that gets us some amount of sig figs. So we can say, this, since the top has 3 sig figs, I would assume that the bottom would have 3 sig figs. And so we'll put this as like 1 liter like that. And so this is 55.5 moles of water. And then we can do our mole fraction of our solvent. Again, it's going to be our moles of our solvent over the total moles. So we have 2.50 moles of our solute plus 55.5 moles of our solvent, right? And so we are going to get 0.957 as our mole fraction. And then we can go ahead and calculate the vapor pressure of our solution by saying, okay, we take our mole fraction, multiply that by the normal vapor pressure, which it has up there, 23.8 millimeters of mercury, and that will get us 22.8 millimeters of mercury for the vapor pressure of our solution. So there you go. Again, like I said, a little bit of a jump in the beginning, but after you get that bit, hopefully it wasn't too bad. Last one. This one's a little bit trickier, so hopefully I don't run out of room. This one, non-volatile compound B, just something, has molar mass 97.80 grams per mole. How much of that would we need to add to 25 grams of water to produce a solution with a vapor pressure of that? And it says the vapor pressure of water, it gives you that. So we're kind of working backwards this time. Your answer, you can see. If you'd like to try it out, you go for it. Again, it's just kind of working backwards. So our equation is the vapor pressure of our solution is equal to the mole fraction of our solvent times our normal vapor pressure of our solvent. So we are trying to find out, we need to figure out our mole fraction, essentially. We have the normal vapor pressure, and we have the vapor pressure that we want. And we're trying to figure out how much of our solute we need to add to get us there. So we're going to go ahead and solve for the mole fraction of our solvent right now, which is going to end up being the vapor pressure of our solution over the normal vapor pressure of our solvent. So there we go. So that means chi will be equal to 23.756 over 42.362. And both of these are in torr, which isn't going to matter because they're going to cancel out right now. And we get that our mole fraction that we're looking for is 0.5608. And so that is how much, that is the amount of kind of via moles of our solute we need to add to get us there. So we know how much water we have, right? And this, like I said, this is a mole fraction. So even if you were lost here, what I would do then is, okay, we know we have a mole fraction and I have grams of water. Probably at some point I'm going to need moles of water, right? So let's go ahead and convert our grams of water into moles of water. Okay, so we get, 13.88 moles of water. Okay, so let's go think about what we know about our mole fraction, right? We have our mole fraction, and so our mole fraction is the mole fraction of our solvent, which means it's moles of solvent over total moles. So moles of solvent plus moles of solute, right? Okay, so but now we have the moles of our solvent, so we can go ahead and solve this for moles of our solute. So we have, plugging this in, 0.5608 is equal to our moles of our solvent over our moles of our solvent plus moles of our solute. So now it's just kind of a fun with math thing, right? We can multiply the denominator by both sides, which gets us, let's see if I can, just worried about room. Let's divide this in half. We'll go up here. So we get 0.5608 times 13.88 plus moles of our solute is going to equal 13.88. We divide both sides by 0.5608, and then we'll subtract 13.88, just kind of getting us a little bit ahead, and we're going to get that our moles of solute, once you finish rearranging this, will equal 10.87 moles. And so now we have 10.87 moles of our solute. We have the molar mass of our solute, even though we don't know what it is, right? We have our molar mass, and so we know, okay, for every 1 mole of our solute, we have 97.80 grams of our solute, and we can multiply those out and get this ridiculous, right, amount of our solute. So this is just kind of working backwards. The tricky part, I would say, is like this step, right? Plugging things in to solve for our moles of solute so that you can use your molar mass and calculate all of that out. One last kind of topic for today is this modified Raoult's law. So when we were just talking about Raoult's law, which is all of this stuff, this is Raoult's law, okay? But we have a modified Raoult's law in which both of them are now liquids. Okay, so this initial Raoult's law that we were the normal one, that would be when one of them is a solid and the other one is a liquid. We use a modified Raoult's law in which both of them are liquids, or both of them are volatile. Pretty much, if it's a liquid, it's probably going to be volatile. If it's a solid, it's probably going to be non-volatile. And I would specify liquids or solids, right? And I will specify volatile or non-volatile. But our modified Raoult's law is to get the total pressure. So this would be like the pressure of our solution. We are going to do for each one the partial pressure of A times the partial pressure of B. And if you remember from when we did gas laws, the way that we calculate these partial pressures is going to be the mole fraction of A times the normal vapor pressure of A plus the mole fraction of B times the normal vapor pressure of B. Okay. And then if you had 3 things mixed together, you could do mole fraction of C times the normal vapor pressure of C for as many things as you have. Usually you just do 2 though. So this is for the modified Raoult's law. This is if both are volatile. And like I said, usually if both are volatile, both are probably liquids. Just remember that the mole fractions, this can save you sometimes. The mole fractions, if you add them up, they're always going to be equal to 0, to 1. For as many zeros as you need. But they're always going to be equal to 1. So that'll help you out sometimes. Let's try one. So this problem says, using the data below, calculate the vapor pressure of a chloroform benzene solution at 25 degrees Celsius, which contains 50 grams of chloroform and 50 grams of benzene. And you have the vapor pressures, like the normal vapor pressures of those both listed below. So again, our equation that we are using is that we're solving for the vapor pressure of our solution. So we need the partial pressures of, if we think of A and B, let's say, this one's A and this one's B, or whatever the case may be. So that means you're going to need the mole fractions times their normal pressures, right? Which we have these. We have these normal pressures here. But we don't know their mole fractions right now. So we need to go through and calculate the mole fractions. But you have grams of each one, so you can turn grams into moles, calculate their mole fractions, multiply them by their vapor pressures, add them together. So that's what we're going to do. So here I've kind of written it out. So we take our 50 grams of our chloroform, we'll divide that by the molar mass, and we will figure out moles of our chloroform. And we do the exact same thing for our benzene, divide that by the molar mass, and we will get moles of our benzene. So once we have moles of each thing, we can go through and calculate it. Okay, well, things are flying in different orders. All right, so our mole fraction of our benzene will be moles of benzene on the top divided by our total moles on the bottom. So you just add them up. And then the moles of the chloroform will be, the mole fraction of our chloroform will be our moles of chloroform over our total moles and then divide those up. So again, you can always double check these. These should add up to 1. If they don't add up to 1 or something pretty darn close to 1, you've done something terribly wrong. Go back, fix it before you move forward. And then to get our total vapor pressure, or our vapor pressure of our solution, you're going to take the mole fractions of each one of those and multiply them by their normal vapor pressures. So we'll take the mole fraction of benzene, multiply its normal vapor pressure, and then we'll take the mole fraction of chloroform, multiply by its normal vapor pressure, get both of those, add them together, and you will get your answer. So it's similar to Raoult's law. You're just kind of doing everything twice now because you have 2 liquids. You have 2 normal vapor pressures to deal with. So you have 2 that you need to modify in this modified Raoult's law. And that's it. That is the end of chapter 13. So work through lots of these problems, especially the boiling point elevation and freezing point depression problems. You have a lab on that. And then please send me any questions you have. Otherwise,